The next idea that I want to talk about is called infinite series. This idea is based on the ideas that we've talked about previously in this way. We start off with a sequence of numbers in the usual way A1, A2, A3, and so on. We may sometimes start with index 0, so depending on the application, there might be an A0 as well. From this sequence, we're going to build up a new sequence. The entries in this new sequence we'll call capital S with an index, and we'll define them to be sums of these A numbers. We won't use all of the A numbers in any one of them, though. We'll only use part of the A numbers. Therefore, we'll call these numbers partial sums. S number 1 will just be A number 1. S number 2 will be A1 plus A2. S number 3 will be A1 plus A2 plus A3, and so on and so forth. If K is a positive whole number, S number K, partial sum number K, will just be what I get when I add up all of the numbers A1, A2 through AK. These S numbers, S1, S2, and so on, are numbers. So this forms a new sequence of numbers. A natural question to ask ourselves is, does this sequence of S numbers converge to something? If this limit of the SK numbers exists, meaning, remember, an actual honest to goodness real number, then I'm going to give it a special name. I'm going to call it this. I'll call it the sum I equals 1 to infinity, a number I. And I can't emphasize this enough. This actually is a limit. It is not obtained by taking this expression and setting k equal to infinity, because that doesn't even make any sense. If this limit exists, we give it this name, and we say that the infinite series based on the AI numbers converges. If this limit doesn't exist, we say that the infinite series doesn't converge or that it diverges. The simplest case of all possible infinite series is what is called geometric series. For our purposes, I'm going to think of having two numbers, a and r, neither of which is 0. In this case, it's more convenient for me to start counting at index 0. So my first partial sum is going to be S0. Then I'll have S1 and S2, and so on. Partial sum number 1 is going to be A plus A times R. This is what you had for S0, except you take the last term of S0, A, multiply it by R, and add that in as well. S number 2 is going to be A plus A times R plus A times R squared. S number 2 is the same as S number 1, except I take the last term in S number 1, multiply it by R to get A times R squared, and then include that as well. S number 3 would be A plus AR squared plus AR cubed, and in general, S number K will have all such terms out to the A times R to the K power, which, if I wanted, I could write it symbolically using the sigma notation. The reason it's convenient to start indexing at 0 is the index on the partial sum matches the power of R that shows up at the end of one of the partial sums. What we don't know at this stage is whether this infinite series converges or diverges. Does it depend on the A? Does it depend on the R? we'll have to figure this out. The infinite series is the limit of all of these ordinary algebra sums as the number of terms is allowed to become indefinitely big. These infinite series are limits, and as we know, limits can be tricky. We want to begin to look at the behavior of these partial sums as the k tends to infinity. It's important to understand two things. Number one, each partial sum is an ordinary algebra sum of a finite number of terms quantity. That means that all of the rules of algebra are still valid. Secondly, I can't get what I'm after just by sticking k equal infinity into this expression. That won't tell me anything. So I'm going to look at partial sum number k, a plus ar out to a times r to the k power. I'm going to multiply that ordinary sum by r. This is going to have the effect of supplying an extra factor of r to each one of the terms. In r times s number k, the first term is going to be a times r. The last term is going to be a times r raised to the k plus 1 power. The term that is immediately before that one would be a multiplied by r to the k power. So let's write that down. I've written down the terms that I just mentioned a moment ago. I've written them in a slightly staggered format so that similar terms are above each other in both the expression for sk and r times sk. Since these are just ordinary sums, I can do algebra on them. I'm going to subtract the second equation away from the first equation. In the first equation, there is an a. There is no a term in the second equation, so I'll just write down a again. The next term, ar minus ar, is 0. The next one after that is ar squared minus ar squared. So those cancel out as well. And in fact, lots of things cancel out. The a times r to the k minus a times r to the k cancels out. And then there is no r to the k plus 1 term here. So when I subtract this second equation away, I still need to write down minus a times r raised to the k plus 1 power. Obviously, I can factor an sk out over on the left. Sk multiplied by 1 minus r is this number a minus a multiplied by r to the k plus 1 power. For the moment, I'm going to presume that r is not equal to 1. If that's the case, then 1 minus r isn't 0, and I can divide through by the 1 minus r. By doing this, I've actually managed to get a formula for partial sum number k. In this term, the letter k doesn't appear, so this term is the same regardless of which partial sum I'm looking at. A over 1 minus r doesn't have any k in it, so as far as taking the limit as k tends to infinity, I'll regard that as a constant factor in this second term. The only thing that has k in it at all is that quantity. I want to take the limit as k tends to infinity of s number k, constant term, constant factor. Everything is going to be determined by how that number acts as k becomes indefinitely big. I think it's pretty clear that if r is sufficiently close to 0, powers of r will tend to 0. If the absolute value of r is less than 1, then r to the k plus 1 tends to 0. I think it's also obvious that if r is bigger than 1, then r to the k plus 1, at least in absolute value, has to become indefinitely big. If r is strictly less than 1 in absolute value, this term tends to 0, and I'll just have the a over 1 minus r left. If r has absolute value bigger than 1, then the magnitude of r to the k plus 1 blows up on me, and I get divergence. Except for the case where r is exactly equal to 1, we now know when a geometric series is going to converge, and if it does converge, we know what it converges to. If r is equal to 1, then S0 is a, S1 is 2a, S2 is 3a, and since we presumed that the a wasn't 0, those numbers become indefinitely big if a is positive, or indefinitely negative if a is negative. In either case, the limit of the partial sums fails to exist, and the infinite series diverges. So the infinite series, the sum I equals 0 to infinity, a times r to the I power, it converges to a over 1 minus r if absolute value of r is less than 1, and diverges otherwise. In a certain sense, then, we now know everything there is to know about this kind of series. Let's look at an example or two. Let's look at the geometric series 7 plus 7 times 2/3 plus 7 times the square of 2/3, and so on and so forth. I'll identify the a's being 7, the r's being 2/3, and since the absolute value of r is less than 1, I know this infinite series converges. Moreover, I know that it converges to a divided by 1 minus r. As another example, let's look at what's called Zeno's paradox. The idea is that if you walk 1 mile per hour, it's impossible for you to walk a mile. The premise of this is before I can walk the mile, first I have to walk half of a mile. I have half of a mile remaining to walk, but before I can walk this remaining half of a mile, I have to walk a quarter of a mile to get to the middle of my trip to the end. So I would have to use up that much time. But before I can complete the remaining 1/4 of a mile, I would have to do an additional 1/8 of a mile, and then 1/16 and 1/32 and 1/64, and so on and so forth. The reasoning was that because I have to do an infinite number of things, each one of which takes a finite amount of time, there'll never be enough time to walk the 1 mile. Obviously, this is wrong, and the problem was that the person advancing this thought, Zeno, didn't have a good grip on this whole infinite thing. If you look at this kind of thing, this is an infinite series. It's a geometric series. The first term is 1/2, and each additional term is 1/2 of the previous term. A is going to be 1/2. R is also going to be 1/2. A over 1 minus R is 1. Even though there'll be an infinite number of things to add up, and they're all positive, the sum comes up finite, equal to 1, just as you think it should be. As another example, let's think about these partial sums. 0.9, 0.9 plus 0.09, 0.9 plus 0.09 plus 0.009, 0.9 plus 0.09 plus 0.009 plus 0.0009. The first one is 0.9. The second one is 0.99. The third one is 0.999. The next one has a decimal point and 4 nines after that. I think it's pretty clear what partial sum number k is going to be. Partial sum number k is going to be 0 point, and then there are going to be k digits written down, each one of which is a 9. If I take the limit of this as k tends to infinity, what I'll get, assuming that what I'm about to write down even makes sense, is this. This is a geometric series with a equal 0.9 and r equal 1/10. This actually does make sense. It's a geometric series where absolute r is less than 1. In partial sum number k, I have k nines after the decimal point. If I allow k to tend to infinity, that means I have an infinite number of nines after the decimal point. I could have just written this as 0.9 with a little bar above the 9, indicating that it repeats forever. Obviously, this number is fairly close to 1. Some people would say that it's infinitely close to 1, which, if you think hard about it, doesn't make a whole lot of sense. I want to use my geometric series idea in order to figure out how close this number is to 1 in terms of actual difference. Using a equals 0.9 and r equals 0.1, a over 1 minus r ends up being 0.9 divided by itself, which is 1. The sum of this infinite series we were speaking of, which, writing things out, was a decimal point and an infinite set of nines, that number actually is very close to 1. It's so close to 1 that it is the same number as 1. These two numbers are exactly the same number. So I would prefer to describe the situation that way. It is a little bit disturbing. We're used to thinking of numbers as having a single decimal representation, but it turns out that it isn't true. As my last example for a geometric series, I want to think about this situation. I've got a floor and a rubber ball starts off 10 feet off the floor. It's allowed to fall and then bounce upwards again. On each bounce, though, it can only rise to a height that is 80% of its previous height. And I want to figure out the total distance that the ball is going to travel. So initially, it's got to fall down 10 feet. When it hits the ground, it's going to bounce upwards, but it's not going to bounce upwards by 10 feet. It's going to bounce upwards by 80% of 10 feet. So it will travel a distance 10 times 0.8 on the way up from the first bounce, but from there, it has to fall that same distance back down again. When it hits the ground the second time, it's going to bounce upwards, but it's not going to bounce up 10 feet or 80% of 10 feet. It's going to bounce up 80% of 80% of 10 feet. It's going to bounce up 10 times 0.8 squared. And then from that height, it will have to fall that distance back down again. After this bounce, it rises to a height of 10 times, that is, 0.8 to the third power, and then falls back down 10 times 0.8 to the third power, and then this pattern repeats itself. Obviously, up to the number of terms that I've written down, I can simplify this a little bit. This is 10 plus, I might as well combine these together and say 20 times 0.8. These two, I might as well combine them as well and say 20 times 0.8 squared. Then I'll have 20 times 0.8 cubed, and then allowing for this first bounce and calling k the number of up and down bounces of the same height that we've done, plus 20 times 0.8 raised to the k power. This is going to be what I get after the initial bounce, and then k bounces of going up and then down the same height. An observant person will notice that although this isn't exactly a geometric series, it resembles one a great deal. This is a finite algebra sum. I'll think of this as being partial sum number k. This is going to be 10 plus 20 times 0.8 plus 0.8 squared plus 0.8 cubed, all the way out to 0.8 raised to the k power. This is a constant term. This is a constant factor. If the limit of the thing in the bracket makes sense as k tends to infinity, then I will have a formula for what's in the brackets. I'll multiply that by 20, I'll add 10, and I'll have the total distance traveled. I could have factored out a 0.8 out of everything in the bracket as well. If you look at the thing inside the bracket, as k tends to infinity, this is obviously a geometric series. The a is 0.8, and the r is also 0.8. I know that that converges, and moreover, I know that it converges to 0.8 divided by 1 minus 0.8. And doing the arithmetic, I found out that taking the limit as n tends to infinity of partial sum number k, the total distance traveled of the ball is 90 feet. Continuing my effort to keep these things fairly short, I want to think about one other thing right now, and then in the next video, we'll talk about certain other issues. For right now, though, suppose that I have an infinite series, the sum I equal 1 to infinity of a number I, that converges. By that we mean when you look at the partial sums, as you increase the index, the partial sums approach some particular number. I'm going to call that number capital A. Think about partial sum number k, which is the sum of all AI numbers, where I goes from 1 to k, but then also think about the immediately preceding partial sum. That one will be A1 plus A2, stopping at a number k minus 1. These two formulas differ only by the presence of a number k in the first one. So if I look at sk minus sk minus 1, that's actually equal to ak. These partial sums, though, as a sequence of numbers, converge to capital A. If I look at how the difference of the partial sums act as the index tends to infinity, since both of those limits individually exist, it's legal to break the limit of the difference into the difference of the limit. If either one of those didn't converge, though, it wouldn't be legal to say this. Here, I'm looking at a partial sum and I'm allowing its index to become indefinitely big. That limit is equal to A. In this one, I'm taking a partial sum and I'm letting k tend to infinity, which means k minus 1 also tends to infinity. This second limit also exists and is also equal to A. A minus A is 0. This tells me that the limit, as k tends to infinity, of sk minus sk minus 1 is 0. But on the other hand, another name for sk minus sk minus 1 is a number k. So this tells me that the limit, as k tends to infinity, of a number k must be 0. If I have a series, an infinite series, limit of partial sums, if that infinite series converges, then I know something. I know that the individual terms that I'm adding up must tend to 0. We'll see something very interesting about this in the next video. Until then, I hope that everyone's having a good day, and I'll talk to you again soon.